Now you're asked to graph 1 over v and 1 over v squared on the same set of coordinate axes. 1 over v and 1 over v squared are easy to graph. If p is here, v is here. If v equals 1 here and p equals 1 here, then this point is going to be on both graphs. If v is 1, then 1 over v is 1 over 1. V squared would also be 1, so you'd have 1 over 1. So we go through the point 1, 1. Now, if v goes to 2, then you have a difference. 1 over v becomes 1/2. So if this is 1, well, 1/2 would be about here, so we'd have this point on the graph. For 1 over v squared, we're going to do 1 over 2 squared, which is 1/4. So it's only going to be 1/4 as high. So we're going to have a point here on the graph of p equals 1 over v, giving us a graph that looks something like this. And a graph of p equals 1 over v squared that goes through this point and this point. And also, to see what happens on this side of 1, let's evaluate 1 over v for 1/2. We get 2. So we have the point 1/2, 2 on the graph of 1 over v. On the graph of 1 over v squared, 1/2 squared is 1/4, so 1 over v squared would be 4, so the graph would be twice as high as this, and we can't really get there and stay on the screen, but the graph goes up more steeply. So the graph of 1 over v squared is steeper on this side of the 1, 1 point and less steep on this side. The graph of 1 over v is less steep here and here. So the graph of the 1 over v squared is just basically steeper everywhere. It approaches the horizontal axis more quickly, and it approaches the vertical axis actually more slowly. Okay, so those should be familiar characteristics. Now I've got some other stuff on here, but let's not worry about it yet. Let's do this in order, because I asked you then to calculate the area between v equals 1 and v equals 2. Now, that's for both curves. For the 1 over v curve, that area would correspond to the area in this region here, and that's been shaded. Again, the shading's a little harder to see now. And then in a different color, I shaded the region under the 1 over v squared curve, which is clearly less than the area under the 1 over v curve. Let's see how the integrals work out. The area, of course, is just going to be the integral from v equals 1 to v equals 2 of 1 over v, or 1 over v squared. And those integrals are very easy to do. I'm not going to go through the details. We get the natural log of 2, which is about 0.7. For the 1 over v squared, we get a negative 1 over v evaluated between 2 and 1. That gives you 1 minus 1/2, or 0.5. That's very consistent with the picture we have here. This is about 40% greater than this, and this area here looks like it's very plausibly about 40% greater than this area. Actually, I've got this curve a little high. It looks a little more than 40% to me, but you get the idea. Now we want to consider what happens if we have a quick expansion. If I seal off the end of this tube, right now just holding my thumb over it, and heat up the gas, I'm going to build pressure. If I then release that gas, there's going to be a very quick expansion. Now let's imagine that I'm releasing the gas not out into the atmosphere, although we could deal with that, but let's say I'm releasing it into some sort of a air bladder. Think of a balloon that builds very little pressure. In that case, the expansion is going to happen very quickly before any heat can be exchanged with the room. Okay? Now, if you go to the gas law, you'll see pretty easily that that's going to result in a decrease in the temperature. Well, in a quick expansion we call adiabatic. Now, adiabatic doesn't necessarily have to be quick, but typically adiabatic is what happens with a quick expansion. Because in a quick expansion, there's no heat energy enters or leaves the system. So adiabatic means no heat energy enters or leaves the system. In a quick expansion, typically, quick expansion just about has to be adiabatic. Unless, of course, you're like exploding fuel in a system. Okay, but then there's, well, let's not worry about that. Okay, so no heat energy exchange. That's what adiabatic is. The kind of quick expansion I described with the model is typical of an adiabatic expansion. In that case, we have PV to the gamma is constant. I did cross that T, but it's kind of absorbed into the S there. Okay, and we might derive this later. It's not a particularly complicated derivation, but it's a little bit sophisticated. But for right now, this is the rule for an adiabatic expansion. Now that contrasts with PV equals constant, which is what we did in previous examples, and that would be at constant temperature. As I've asserted, at least, in an adiabatic expansion, you're expecting the gas to change temperature, and you're expecting it actually to lower if it's an adiabatic expansion. You can also have an adiabatic compression. Quickly compress the gas, temperature is going to go up. In either case, PV to the gamma is going to remain constant, and gamma is Cp over Cv, the ratio of specific heat at constant pressure to specific heat at constant volume. And you should think through what gamma would be for air. You've had that information. Air being diatomic, Cp is 7/2 R, Cv is 5/2 R, so the ratio would be 7/5. In that case, P is going to equal 1 over V to the gamma. So P is constant over V to the gamma. If the constant happens to be 1, then P would be 1 over V to the gamma. If gamma is 7/5, which is 1.4, then we would have the curve here, P equals 1 over V to the 1.4. Where does that curve lie with respect to the others? Now, this is just motivation for why we have in the posted question why you're asked to do P equals 1 over V to the 1.4. Well, 1.4 is between 1, which is the power of V in the denominator here, and 2. Okay, so we expect that curve to lie between the 1 over V curve, well, the 1 over V curve here, I just traced the wrong one, and the 1 over V squared curve here, and probably a little closer to the 1 over V curve, but there's some nonlinearities, and we're not completely sure of that, but let's draw it that way anyway. So this green curve is your P equals 1 over V to the 1.4 curve. And we could do that integral, and that integral will be quite easy to do, and we'll continue in the next clip.